Hello everyone, welcome to the second part of this series on ACSL of computer number systems, which is the first contest of the Elementary Division. So today we'll be going over addition and subtraction of all the number systems, some word problems with the number systems, RGB hex codes, which is very interesting, we'll look at it in a little bit, and some sample questions from the ACSL tests. So let's start with addition and subtraction. Addition and subtraction are the only operations you're going to need for number systems other than decimal. You'll normally want to convert it to decimal if you have to multiply or divide it. So you'll only need to remember how to add and subtract. So starting with binary addition, first problem that we have is 1101 plus 110. 1 plus 0, that's normal, that's just 1. 0 plus 1 is also the same, so it's 1. And now here's where it gets different, because 1 plus 1 would normally be 2, but you can't use that. It's actually equal to 1, 0, so we put a 0 here and carry a 1 on top. And then again, that's the same thing, 1 plus 1, let's put a 0 here and add a 1. So 1101 plus 110 binary is 10011 binary. Now let's move on to the second problem. So over here it's 0 plus 0, which is just 0, and now 1 plus 1, like we just did in the previous problem over here. We put a 0 down here and add a 1 on top. 1 plus 0 plus 1, again we do the same thing, add a 0 here and put a 1 here. Now here's where it gets a bit different. 1 plus 1 plus 1. That means it would normally be equal to 3. But 3 is equal to 1, 1. So that means we add a 1 down here and carry a 1 up to the top. So that means it would actually become 2 1s, because there's 2 zeros here. And again, we have 2 1s, which means 0 and 1. And again, we have 2 1s, so just add a 0 and then put a 1. So 11011010 plus 10110 binary is equal to 10011000 in binary. Now let's move on to binary subtraction. So this time it's 1101 minus 110. So 1 minus 0 is 1. There's nothing to be minused. Then 0 minus 1, here we have to borrow. This becomes a 0. This becomes 1, 0. This isn't just 1, it's actually 2. So that means 2 minus 1, it's actually 1. And then this is a 0 over here since we borrowed, so this becomes a 0, and we add a 1 here. So this becomes 1, 0. 1, 0 minus 1 again is 1. So 1101 minus 110 is 111. Let's move on to the other one. Oh, sorry, this is supposed to be a subtraction sign. So, excuse me. So now this is actually a subtraction problem, not an addition. So 11011010 minus 101110 binary. So 0 minus 0 is 0. 1 minus 1 is also 0. And now over here we have to borrow again since it's 0 minus 1. So that becomes a 0. This becomes 1, 0. And then 1, 0 minus 1 is just 1. Then over here, 0 minus 1, we can't borrow from this 0. There's nothing there. So we borrow from here. This becomes a 0. This becomes a 1. This becomes 1, 0. And again, we have to borrow. So this remains a 1. And then this becomes a 1, 0. So 1, 0 minus 1 is 1. And 1 minus 0 is also 1. And again, we have to borrow from here. This becomes a 0. Then 1, 0 minus 1 is 1. So 1, 1, 0, 1, 0, 1, 0 minus 1, 0, 1, 1, 1, 0 binary is equal to 1, 1, 1, 1, 0, 0 binary. Now let's move on to octal addition. So the first example is 241 plus 173 octal. So we have a table on the side over here. So 1 plus 3 is 4. It's normal until the digit 8, remember? So it's just 4. And then 4 plus 7. Now that's more than 8. So that will get a bit different than what you're used to. We skip 8 and 9. So it'll actually end up being 13, not 11, because we skipped 2 digits. So we write a 3 here and put a 1 on top. Now 1 plus 2 plus 1 will be the same as normal because it's not above 8. So 241 plus 173 octal is 434 octal. Let's move on to the second example. 7423 plus 4725 octal. So 3 plus 5, that'll normally be 8, but we skip 8 and 9, so it'll actually be 10. But it's not 10 exactly, it's 1, 0, since 10's value in decimal is actually 1, 2 in octal. So we put a 0 down here and a 1 up there. So 1 plus 2 plus 2 was 5, that's normal. Now 4 plus 7, we just did it in the first example. It would normally be 11 over here, but it's actually 1, 3. So write a 3 here, put a 1 up. And again, now this time it's 7 plus 4, but we have an extra 1 up here. So it'll be 1, 3, but we have the extra 1, so it'll be 1, 4. So 7423 octal plus 4725 octal is 14350 octal. Now let's move on to octal subtraction. 241 minus 173 octal. So 1 minus 3 is not possible unless we go to negatives. So we borrow from here. This becomes a 3, this becomes a 1, 1. And this is a 1, 1 octal, so it's actually just 9. It's actually 9 minus 3. So it's actually, the output is actually 6 because remember we are skipping 8 and 9 here, so it'll be 2 more than normal. So instead of 11 minus 3, 8, it'll be 6. And now 3 minus 7, we have to borrow again. This becomes a 1. This is 1, 3. And again, 1, 3 is actually just 11. So 1, 3 minus 7 would normally be 6, but it's actually equivalent to 11. So it's actually 11 minus 7, which is 4. And now 1 minus 1 is just 0. So 241 octal minus 173 octal is 46 octal, or 046 octal. Now let's move on to the second example, which is 7423 minus 4725. So 3 minus 5 again is not possible. We have to borrow. This becomes a 1. This is 1, 3. 1, 3 minus 5 is possible, but 1, 3 is actually equal to 1, 1, so it'll be 6 and not 8. So now 1 minus 2, again, we have to borrow. This becomes a 3. Sorry for the delay. So this is a 1, 1 now. And 1, 1 is actually equal to 9. So it'll be 9 minus 2 and not 11 minus 2. So it's actually equal to 7. So we put 7 here. Now 3 minus 7, we have to borrow again. This becomes a 6. This becomes 1, 3. Yet again, 1, 3 is not equal to 13. It's 11. So 11 minus 7 is 4. So this is a 4. And then 6 minus 4 is normal. 2, 4, 7, 6. So 7, 4, 2, 3 octal minus 4, 7, 2, 5 octal is 2, 4, 7, 6 octal. Now let's move on to hexadecimal addition. The first example we're taking is 2ab plus 1c3. So b plus 3, would be 11 plus 3, which is 14. 14 is equal to e. So this is e. And then a plus c will be pretty high since it's 10 plus 12. 10 plus 12 is 2, 2. Over here, this is 2, 1, which is equal to 1, 5. So we can safely assume that 2, 2 would be 1, 6. So we put a 6 here and a 1 here. Now 1 plus 2 plus 1 is normal. That's just a 4. And over here we write 1, 6. So 2ab plus 1c3 is 46e hexadecimal. The next example we're taking is 3da plus 1e4 hexadecimal. A plus 4 is 10 plus 4, that's just e. And then d plus e is 13 plus 14, that's 27. We can assume that would be 6 more than 21, which is 1, 5, as you can see on the table on the right. So 1, 5 plus 6 would normally be 2, 1, but this is hexadecimal, so it's actually 1b. So we put a b here and 1 here. 1 plus 3 plus 1, that's normal. It's 5, so 3da hexadecimal plus 1e4 hexadecimal is 5be hexadecimal. Now let's move on to some hexadecimal subtraction. The first example we're taking is 2ab minus 1c3. So b is equal to 11, as you can see in this table. So 11 minus 3 is equal to 8. And remember, it's the same until the digit 10, so we'll just write 8. Now a minus c. A is less than c, so we have to borrow from this 2 here. It becomes a 1, and this becomes 1a. 1a is a plus 1, 0. 1, 0 is over here is equal to 16. So 16 plus a is equal to 10, so 16 plus 10 is 26. So this is basically 26. And then c is equal to 12. So it's 26 minus 12, that's 14. 14 is equal to e. So write e here. Now 1 minus 1 is just 0. So 2ab hexadecimal minus 1c3 hexadecimal is e8 hexadecimal. So now moving on to the second subtraction problem. 3da minus 1e4. A is 10. 10 minus 4 is 6. And remember, it's the same until 10, so don't need to worry about that. And over here, borrow from the 3. This becomes a 2. So 1d now. And like we just did, 1a is 26, because that's 10 plus 16. D is equal to 13, so it'll be 29. So 29 minus 14, which is e, is 15. 15 is equal to f. It's equal to f. And 2 minus 1 is 1. 1f6 hexadecimal. 3da minus 1e4 is equal to 1F6 hexadecimal. So that's it for the addition and subtraction of the number systems. So now let's move on to word problems. Just taking a couple word problems. So first one, if you're living in a hexadecimal world and F26A people vote for one candidate and EB72 vote for another, how many people voted in the election? That's a simple hexadecimal addition problem since it's asking us how many total people voted. So it'll be F26A plus EB72. We just have to figure out how many total people voted. So A plus 2, that's A plus 2 is C, and 6 plus 7 would normally be 13, but 13 is represented by D. Now 2 plus B is also represented by D because B is 11. Now F plus E, F is equal to 15, E is equal to 14, so F plus E is 29 in decimal, so 16 is 10 in hexadecimal, so if we take the difference of that, then it will be 1, a digit over here, and then 13 in the blank space that I have left here. So it's equal to 1DDDC. So 1DDDC hexadecimal people voted in the election. You live in an octal world. It's the year 2025. When's the next leap year? Leap years are still in 4 decimal years. So first of all, we have to convert 2025 to decimal to find out how many decimal years it will be in. So 2025, if you remember from the first video I made, we write it vertically to convert it and then multiply it by the base, which is octal, so it'll be 8. And it's varying powers, it's exponentially greater, so it starts from 0, then 1, then 2, then 3. So 8 power 0 is just 1, so it'll just be equal to 5. 8 power 2 is, 8 power 1 is just 8, so 8 times 2 will be 16. 8 power 2, it's 64, but it doesn't really matter since we're multiplying it by 0, so that'll just be 0. And now 8 power 3, that's just do the math, it's 512. So 512 times 2 is 1024. Add it up, and we get our answer of what it is. So it's actually the year 1045 in decimal. So now we have to figure out when the next leap year is. Leap years are every 4 decimal years, so every 100 is divisible by 4, so we just have to see the next multiple of 4 after 45, which is 48, so it'll be 1048. And now we convert 1048 back to octal. Since you live in an octal world, you need to know the octal value of it. So now, for that, if you remember, we have to divide it. 1048 by the base, which is 8. Now we can just do the math. is normal long division. And again, keep doing this until we get 0. So our quotient is 131. Our remainder is 0. So we label this as R1. So R1 is 0. So just write it here. And we got 131. So we can write 131 here. And now again, we divide it by 8. So again, we're just using normal division, long division. So it's very simple. And now R2 is 3, and our quotient is 16. Let's just write it from the bottom so that we can just say it top to bottom at the end. And our quotient was 16. So 16 divided by 8 is 2. Remainder is 0. So now we can, 2 is not divisible, 8 can't be put into 2, so any number of times, so we just, if we did that again, remember we have to get a quotient of 0, and we'd get a remainder of 2 and a quotient of 0, so it's 2030. So the next leap year is in 2030 in your octal world. So now let's move on to RGB codes. So RGB color code, or RGB color system, constructs all the colors from the combination of red, green, and blue colors in a hexadecimal code. The colors have brightness levels from 0 to 255. This makes 256, x256, x256, 1677216 possible colors. That's 16,777,216 possible colors. RGB is equal to red, green, and blue in the acronym. So the first 2 digits in the hexadecimal code will be the red component, the next 2 will be green, and the last 2 will be blue. So there's a diagram over here. So first of all, we have to figure out what brightness these are. These are all at max brightness, and the reason we know that because together, when all of these 3 are combined, it makes white, which white is all the light combined, like rainbows, which have every single color in them, are split by white light that's split into different colors. So we know that these are max brightness. And over here, there's no green over here. So red and blue at max equal this purplish pink. Red and green at max with no blue equal yellow. And green and blue at max with no red equal this turquoise-ish shade. And since this is only one of the brightness levels, there's actually 255 more, which means there's a lot of other colors that will be there. All you really need to know is which components are which, so you just have to remember that the first 2 digits are red, next 2 green, and last 2 blue. Now let's move on to some sample problems from past ACSL tests. So we have an RGB question first. What is the difference between the blue component of the color A2B3C4 and the color 3F2E1D in hexadecimal? So the blue component, if you remember, is the last 2 digits. So these two digits and these two digits. So it's C4 minus 1D. So 4 minus D, we have to borrow. D is 13. So this becomes a B. This is 1, 4. And now D is 13. 1, 4. 1, 0 is 16. So it'll actually be 2, 0. So 2, 0 minus 1, 3 is 7. And remember, if it's as low as 7, if it's lower than 10, then it'll be the same as decimal. So now B minus 1, that's normal, it's just A. So the answer is A7. C4 minus 1D is A7. You just, mostly, all you have to remember is how to subtract hexadecimal and which components they are. You don't really need to remember any other things about RGB hex codes. Let's move on to another sample problem. Evaluate the following expression and write your answer in base 10. The small numbers on the bottoms are the bases, so this is octal, this is binary, this is hexadecimal, this is decimal, and this is binary. So follow order of operations. First we do the parentheses, and inside the parentheses first we do the multiplication. So 1, 1 binary is equal to 3 in decimal, if you remember. So it's 3 times, we have to convert 1, 4. So 1, 4, 4 times 16, but its power is 0, so we can just write that as 4, because anything power 0 is that, is 0 is 1, so it'll just be the number itself. So 1 times 16 power 1. So 16 power 1 is just 16, so this will just be 16. So this is 2, 0. So it's 3 times 20. That's 60. So we just underline this part and put it as 60. And now next, just going left to right, because we have an addition and a subtraction. So octal, 57 octal plus 60. So again, we do conversion into decimal because we don't want to convert into octal and then back to decimal, since we have to write our answer in base 10. So 7 times 8, but it would be power 0, so it's just 7. 5 times 8 power 1, that's 5 times 8. Anything power 1 is the same as the number being exponentialized. So this is just 40, so it's 47. So 47 plus 60 is 107, but 107 minus 57 is 50. So the entire parentheses is 57. No, sorry, 50. So 50 times 100 binary. 100 binary is 4, so 50 times 4 is 200. So, and since we converted all of it to decimal first, we don't have to convert it back to decimal for our answer. Which of the following RGB codes is more red than either green or blue? So basically what it's saying is, are the first two digits larger than the next two or the last two? So for the first one, it starts with A, but the next one starts with F. The next pair starts with F, so it's F is greater than A, so we can immediately cross that off. And then B, it starts with 9, and the last component, the blue component, starts with C, so that's also obviously less. Now, C is so far greater because it starts with A, and the rest start with 3 or 9, so we'll look at that later. And now D starts with 9, and the last one also starts with 9, So let's check that. Now we are looking at the second digit now. Is A greater than C? No, it's not. So we can cross this off too. Just checking. Now for C, is A9 greater than 3F? Yes, because it starts with A. The other one starts with 3. Is A9 greater than 9C? Yes, because it starts with A. That starts with 9, which is one less. So our answer is C. A9 is greater than both 3F and 9C. So now an extra challenge for you to post your answers in the comments. How many ones are in the binary representations of the numbers 1 to 20 inclusive? So in the binary representations of 1, 2, 3, 4, all the way up till 20, how many ones are there? Post your answers in the comments below. And don't forget to like and subscribe. Thanks for watching, and stay tuned.